We have Lena Heimberger, who is going to be talking OPRFs in the wild, a survey of real-world deployments.
Does it work? Okay, cool. So thank you. So the talk today is going to be about OPRFs, how you use them, or how maybe you use them without knowing, and also how you could use them in the future. And maybe to give a bit of an intuition, in case you ever find yourself thinking, oh, I want to send this over a wire, but I don't want to send it in plain or encrypted, so you actually hash it. Or in case you ever wanted to intersect the set privately, which is a bit more of an abstract use case, but imagine you want to host a dinner party with a friend, and you still have to agree who to invite. Or maybe you want to generate unlinkable tokens, like tokens for the +1s your friends are going to bring, so you actually let them into the door. And then maybe you want to host a fully private dinner party where you don't refer to each other by your names, but actually by some MPC-branded deterministic identifiers. Or in general, if you have something that's kind of a low entropy input and you want to get a deterministic high entropy output, in that case, you may want to consider using an oblivious pseudorandom function, or OPRF. In an OPRF, the client has some input X and wants to get the PRF output under a key that the server has. But they don't want to tell each other their inputs. So at the end of an OPRF, the client learns the evaluation, but nothing about the server's key. And the server learns nothing, so nothing about the input or the output. So let's maybe take a step back and talk about PRFs first. So we don't ask very much for a function to be a PRF. We ask that it's deterministic, that it runs in polynomial time, and it is hard to distinguish a PRF output from a randomly chosen output of the output space. And that's relatively weak. So that's weaker than what we ask of hash functions. But what's kind of nice is that we have this additional key. And then if we have something that's low entropy, if the key is high entropy, then the output is also high entropy. And there's a number of ways to construct PRFs. A really simple one is this like two-hash way, where we take the input, hash it to the curve, and then evaluate it with some random scalar that is going to be our key, and then hash the output of that multiplication as well, just to remove the algebraic structure. And that is almost everything we need to get an oblivious pseudorandom function. The only other thing we need is we need to sample one additional scalar on the client side. Then this scalar is used to mask the element we hash to the group. And then the server just faithfully evaluates it with their key. We can unblind it by applying the inverse of our blinding element. And then we have our output, and we just need to hash it again. And that's the 2#DH OPRF. And the nice thing is, even though there's a ton of academic research that covers really a wide area of use cases and properties, like there's extensions and augmentations and post-quantum versions and pre-processing versions, none of them are used in practice, so we already know everything that we need to know for this rather practice-focused talk, which is as far as we know. Maybe we missed something. Okay. So 2#DH OPRFs are actually standardized by the IETF as an RFC. They were also presented to the NIST in 2023 at the multi-party threshold scheme workshop, but they did not make it into the call. So it's not like the threshold signatures, unfortunately. So there's only basically this completed standard. They standardized the 2#DH OPRF that we just saw. They standardize a verifiable variant, where the client also gets approved that a certain key that the server pre-committed to was actually used. And then there's also a partially oblivious variant, where a part of the client input is public, so like a validity period or some additional information. And then this is also a part of the evaluation. That's really useful if you actually want to deploy an OPRF in practice. And maybe you think, oh, but if the client can then verify that a certain key was used, isn't it nicer to use a blind signature? And then the answer is kind of if you don't care that much about computational time, but in a blind signature, everyone can verify that a certain key was used. But just ballparky, it takes roughly an order of magnitude more computation and 3 times more communication to perform a blind signature. And that's kind of where OPRFs are useful, which are these settings where you actually care a lot about latency and performance and have to perform a lot of them. Also, OPRFs are amortizable, so if you repeat a lot of them, this entire issuance step up here, where you compute the OPRF, is way more efficient. Okay, so I said we're going to talk about use cases. We roughly grouped them into 4 different use cases. So there's like unlinkability, protecting low entropy secrets, private set intersection, and deterministic identifiers. And we're just going to go through them now. So getting unlinkability, I think that's kind of like the most widespread adoption of OPRFs, which is privacy pass, where the server allows the client to perform a number of OPRFs with some randomly chosen input. I mean, it could also be a counter, it doesn't matter. But basically, later the client can redeem these PRF evaluations together with the input and, for example, avoid to be rate limited again. And that's kind of like every time you see these I'm not a robot checkboxes, most of the time it's an OPRF or a blind signature behind it. And you have these evaluation and then redemption flows. There's also currently discussions at IETF of using this for media over quick. So for low latency operations, and their OPRFs would be a really good use case. But there's also other use cases where, like there's this privacy preserving search engine called Kagi that kind of gives you a number of tokens that you can then use for the services, and that's also privacy pass behind it. So that's a really nice use case for OPRFs, just getting out some tokens. And then there's, as I mentioned before, this deterministic extraction of something that's high entropy from something that's maybe not that high entropy. And that's kind of like 2 really large use cases. One of them is private set intersection. This works way better if one party has a significantly bigger set than the other party in a client-server setting, or when just one party has a way bigger set. And here, what is party with the bigger set, I just called them the server because it's usually the case, can do is they just publish the PRF evaluations of all of the set entries, which they can do because they have pseudo random. Maybe you just throw some group elements that you randomly sampled in there, why not? And then the client performs an OPRF with the server and can just compare the outputs of the OPRF against their against the server list, sorry. And the reason I wrote down the OPRF is that there is some use cases, none that are deployed, but if you do things like discovering context or something where then you can reason about something like the set size, and you may want to do that, then you want to make sure that the correct key was used, because otherwise it gets segmented into groups. Yeah. Something like context discovery, unfortunately, isn't deployed. What is deployed, and what is probably like the most famous example of private set intersection, is when Google linked advertisement views to purchase history to reason about which ad views actually resulted in being converted to actual purchases. And also Google and Microsoft do compromise credential checking, where basically they see, oh, has your credential been used in a breach, and then outputs a warning. And that's also OPRFs and private set intersection in the background. And then Cloudflare did something that's related. So not only did they check the credential, but they also checked like related credentials. I don't know, like for example, by appending an exclamation mark to the end of your password, you may get a new password after your password expired. And none of the schemes use verifiability. In my opinion, they don't really need them, but yeah, that's something to think about when you do private set intersection. Maybe you need some verifiability. Okay, so let's go to like the final group of OPRFs, which is OPRFs for identification. And there's this really nice protocol, which is opaque, where basically you authenticate yourself without revealing your password. And what you do is, during a registration step, you perform an OPRF with the server, and then get a kind of per server key from your password. And this is really useful because people tend to repeat their passwords, even though they're not supposed to. But in this case, it's not that much of a problem because you have an evaluation of the server key. So if you perform an OPRF with different servers, it doesn't matter because you're going to get a different output. And then using your server-specific key K prime, you just encrypt the secret part of a public-private key pair, store it at the server, and then when you want to authenticate, the server kind of gives you this as a challenge, or just gives you the encrypted secret key. You perform another OPRF. If you did it correctly, you can decrypt your secret key, and then you just perform an authenticated key exchange and authenticate that way without ever revealing your key. This is deployed like in a number of protocols, I think. The only public reference I could find is that WhatsApp uses it to avoid leaking your key if you input your key to your PIN to recover a backup. And then there's this entire relatively new section of computing identities and wallet keys from some output or input in a threshold setting. And in a threshold setting, this just means that we don't communicate with one server, but we communicate with a number of servers. And we need several of them. We already had like a really nice session about that in the morning, so I'm not going to explain it. And there's like, on one hand, there's something that's where it's used in practice, which is to compute from social media handles and phone numbers offenders of sexual misconduct while preserving victim privacy to kind of detect serial offenders. And this is apparently something that's deployed in California. And then there is this, in the last year, there was suddenly a lot of push in the Web3 world to compute identities from OPRF input. So there's MetaMask, which uses it for login. There's Taseo, which, except for me, all of my co-authors are affiliated with, which is deploying their entire network very soon. And they rely a lot on OPRFs. And then there is also Human World, which uses biometric data and then computes using an OPRF, an identifier from this biometric data. And the reason this is kind of like more relevant to this workshop is they very much value MPC friendliness and properties that are a bit newer in OPRFs. And that's what I would like to move on to. And something that's really interesting is that they now care about public verifiability. And you may now say that, oh, so basically we build an OPRF and then make a blind signature out of it, which is what I thought we were doing back when we started working on this. But because we just, in the OPRF evaluation, attach a zero knowledge proof that the correct key was used that can then be verified by anyone. The nice thing is that it is actually both stronger and more flexible than a VOPRF itself, because anyone can verify a zero knowledge proof by tying input and evaluation together. And you can also prove the input without revealing the output, which is very nice in case you have like repeated inputs. So you don't have this, I show you the input and the PRF evaluation anymore, but you can just say, hey, I have a proof here. And in general, the construction of these publicly verifiable OPRFs and blind signatures is very different, and I think should be analyzed independently. And something you really want to optimize for in this case when you prove something is zero knowledge is that you want to have as few constraints as possible, because each constraint adds additional computational complexity. So for example, in RON CS, so in rank 1 constraint systems, every multiplication costs you one constraint, but additions are free. So you generally want to use a cipher with low multiplicative depth. AES and SHA don't count as these. One of them that's actually low multiplicative depth is Poseidon 2. If you use Poseidon 2 instead of SHA-2, you have 2 orders of magnitude fewer constraints in your constraint system, which is really, really nice. And then another example is using a zero-knowledge friendly curve, for example, baby jub. Basically any curve is zero-knowledge friendly when the base field is the same field as the scalar field in the proof system itself. That's the case for baby jub. So there you can directly operate on the points of the curve, and that's really nice because then you don't have to do this really costly translations of the curve points. And the reason I zoomed in so much on Poseidon 2 and baby jub is because we built an OPRF from it. And that one takes 20,000 constraints, which you may think is quite a bit, but it's significantly freer than just proving SHA-256, but you get an OPRF and not just a hash evaluation. And how long does it take to prove like the 20,000 constraints and to do everything around it? It's actually really efficient. So it takes like 1 millisecond to compute the VOPRF, which is twice as long as doing it naively with just the normal 2HDH. But in the threshold setting, it actually scales really, really well. So it takes less than 3 milliseconds for 3 parties. And that's because we use the very non-standardized Poseidon and baby jub. And something else we can do if we use VOPRFs with zero knowledge is that in a trivial threshold setting, we have to verify one proof per party in our threshold setting. But in a recursive setting and using VOPRFs, we can actually aggregate the proofs into one single proof. So the client has to verify a constant number of proofs, which is 1. So there only ever has to be one proof to be verified in a threshold setting. It's a bit of cheating. You have to aggregate the responses by an accumulator who then actually aggregates them. And you have an additional round of interaction in there where 2 rounds actually, like 1 additional challenge and 1 additional response. But you don't need to communicate between the servers, which is why we use the aggregator. It's really nice. So basically, what this does is that even though it's a bit more expensive to generate the proof, it's significantly easier to verify that the proof. So if you have repeated showings, that's actually really nice. So here are some benchmarks. Basically, that's how you do it if it's single server, which is nice. The communication is actually very, very low. And then we have the threshold OPRFs and the threshold verifiable OPRFs, which are still here. So this is microseconds, so this is like 2 milliseconds, which is still all right. And then if you go to the publicly verifiable variant, you kind of need to take like 1 millisecond of client computation, but it's still all under, or just under 1 millisecond, and relatively low communication. So to conclude, OPRFs have a really wide area of application. They're really lightweight, which makes them interesting for anything that's real time. And you can also extend them to give like a really large number of protocols. And using something that's not necessarily standardized, but MPC and zero knowledge friendly, gives us efficient OPRFs and constant verification costs, even in a threshold setting. Yeah, that's it. I still have a bit of time, so this is basically an overview of all of the applications we serve it. Just like with the name. I also wanted to, like, if you reuse your inputs, then sometimes you have to be really careful with verifiability. And then also the application types and the used curves. As you can see here, there's quite a bit of variety. Sometimes, unfortunately, we weren't able to figure out which curves they used. Yeah, so that's it from my side. Thank you very much.
Okay, thank you very much for the talk. Is there any question? I do have a question. So in any of the applications, do you saw anyone caring about adding private metadata to the OPRF?
That's a good question. I don't think so, now that I look at it.
Yeah, it's a long-standing question in application world. Okay, any further question? Okay, let's thank the speaker then. Thank you very much.